Good morning. And some students asked me about homework. So this is it. Not everything you see on a web assign is mandatory. Some things are optional, helpful, but optional. So please tell me what you think about this situation. We have three charges. How do we know? We can count, and lots of information is being provided. This is a review question. What is net force? How do we find it? It is much less about current topic and much more about PY105. And naturally, in physics, the strategy begins from drawing a picture which represents what's happening. And when we read this force, this word force, that immediately tells we have to draw a free body diagram. So we have to recollect what is a free body diagram, how do we draw it, what does it show. And a free body diagram shows all forces acting on the object chosen to be our system. So if we have several objects, first we have to choose which we're going to use for free body diagram. In this situation, we don't have to think. We are told that we have to draw a free body diagram for the second charge. And that's what everybody should be doing right now, having a pen and a pencil and drawing a free body diagram for the charge in the middle. It's a positive charge. Now, when several charges are acting simultaneously, each individual charge is responsible for generating its own individual force. So we can break this situation into two individual smaller subsystems. First, we can consider only the charge on the left and the charge in the middle. And because we can read, we can see they both are positive. And what does it mean? What do we know about charges now? Repulsion, repel each other. So now we have to choose what force we want to draw. We can draw a force acting on the left charge from the middle charge, or we can draw a force acting on the middle charge from the left charge. And the answer is we have to draw forces acting on the object we consider as a system. This is our system. Which means in our picture, this is the object, and we have to draw a force acting on it. From what? From the charge to the left of it. So in general, if we want to draw a vector, this arrow represents the word a system. But if we want to draw a vector, we can draw a vector this way, that way, this way, that way, this way, that way, this way, that way. We also have two symbols for direction into the screen and out of the screen. And in general, could have been even anything else. So out of these 10 arrows, there's one which is correct. All other 9 are wrong. So please tell me, anybody, how should I draw an arrow which represents the force acting on this charge from the charge located to the left to it? To the right. That's what repulsion means. We can imagine a tiny, tiny, tiny numb pushing away. And that's it. That finishes the first part of the reasoning. Now we move on to the next part. The same middle charge, but now we have another positive charge on another side, which is actually much stronger. And now we have to draw a vector which represents the force acting on the same middle charge from the right charge. Well, there are no wrong charges, so. And now, of course, we have to draw it to the left. But if I would finish it like this, would it be representing the situation? No. Clearly, according to the Coulomb's law, the second force should be stronger and arrow should be longer. Why? Well, because the distance in this situation doesn't matter because it's the same for each pair of charges. The only magnitude of each charge matters, and this charge is much stronger than that one, so it exerts a stronger force. Now, step number 3, net force. Well, if I write it just like that, there's a risk I will make a mistake because a force is a vector. This is vector, let's call them 1, 2. This is 2, 3. Same symbols we used for distances. So I can write it like this. And most probably that would lead to a mistake because a force is a vector, it's not a number. And to demonstrate that fact, we usually use a little arrow above. A textbook would use a probably bold, italic font to differentiate a vector from just a number. Now what do? Well, to decrease any risk to make a mistake, we follow the procedure. Next step, we draw the x-axis. Relative to this axis, the same expression now becomes an expression between components. And now, finally, we can start using magnitudes. Because the rule which we use, and everybody else uses in physics and mathematics, says a vector which points in the same direction as the axis has a positive component relative to this axis. So this component is just equal to the magnitude of this force. Plus, we are adding components, so it's a plus. But the second vector points opposite to the positive x direction, which means the actual component of this vector is negative relative to this axis. So we have to subtract eventually two numbers, and the result will be less than 0 because we're subtracting a large number from a small number. And if a component is negative, that automatically means the vector which this component represents must point opposite to the positive x direction. Opposite to the positive x direction means opposite to the right, which means to the left. But of course, we wouldn't have to follow all this strategy if we knew a tail to a head rule, because a tail to a head rule gives the answer immediately. We just have to add an arrow number 1 and an arrow number 2, draw the resultant, look at it, done. So this is mostly a review. How do we add vectors in general? And the answer is net force points to the left. Now let's just calculate some actual net forces. Here we have three charges, distances, and let's calculate net force acting on the charge in the middle. So now I'm going to do it much faster. First, a Freebody diagram. This is the positive charge, and now it's being attracted toward the charge number 2, and it also is attracted toward the charge number 3. So if I want to calculate the net force, before I find the net force, I don't really know how does it point, right? So I don't know if it points to the right. I don't know if it points to the left. So my assumption is net force will point to the right. But eventually my assumption might be wrong or right, depending on calculation. So my assumption is the x component of the net force is positive. How do I calculate it? Well, it has to be equal to the magnitude of a force directed to the right minus the magnitude of the force directed to the left. Now magnitudes. For each magnitude we have the Coulomb's law. And the Coulomb's law says to calculate magnitude we have to multiply several numbers. The constant, the Coulomb's constant, the magnitude of product of two charges, we can use the one magnitude symbol, and the distance between those charges squared minus same constant. Now the magnitude charge number 1 and charge number 3, different pair of charges, divided by different distance squared. Now we can use the numbers. Again, for us, for the constant, we can use 9 times 10 to the 9th. Now, 4 times lecture 1 PY105. This symbol represents micro, which means 10 to the negative 6th, times, well, the order of multiplication doesn't matter. I'm multiplying second and first, so I just look at it from left to right. Times 3 times 10 to the negative 6th divided by distance equals 0.2 meters squared. And now, what did I do? Q1, Q2. What did I do? That's supposed to be 3, that's supposed to be 2. No one said anything. Do you really pay attention? So this is supposed to be negative, because it's a force which attracts the first charge toward the second charge. Now we should add the force which attracts the first charge to the right. So same constant, 3 times 10 to the negative 6 times 7 times 10 to the negative 6 divided by the new distance, 0.15 squared. So one more check. 1, 3, positive. 1, 2, negative. Done. Yes?
Is it better if the radius is
You mean changed, not flipped? Because flipped would look like this. Just saying. And I believe I have the calculation finished, and the number is positive because the third charge is almost as close to the first as second, but much stronger, almost twice stronger, so it exerts a stronger force of attraction. Any questions? Well, let's do one more example. Charge number 2 also experiences two forces. One is from charge number 1, second is from the charge number 3. We have to just repeat the same strategy again. So we start from Freebody Diagram, which demonstrates, indicates, shows forces acting on the negative charge. I'm shifted a little bit so I could draw forces both directions if I need. Now, at the charge number 2. The charge number 1 is positive. That means it attracts the charge number 2 toward itself. This is F. Well, for me, it means force acting on second from first. That's how I read it. But you can use any other subscripts. Now, the charge number 3 is also negative. So it means it repels charge number 2 away from it. So repulsion on 2 from 3. This is the most important part of the reasoning. The rest is a very standard set of steps. If the free-body diagram is correct, everything else almost automatically correct unless you make a mathematical mistake like I did, but fixed. So now we just have to write again that we assume the net force points to the right as the x-axis. And now we are calculating the x component of the net force. And it has to be equal to the difference again. I, at least at the beginning, show explicitly that symbol which says magnitude or absolute value. In any standard textbook, you wouldn't see those vertical bars. Most probably you would see just this. So you would have to know that this symbol in this expression represents the absolute value, a positive number. If you confuse it with a component and use a negative number, that will lead to a mathematical mistake. All right, now what should we write? Constant, which is 9 times 10 to the 9th. We are multiplying two charges, 4 times 10 to the negative 6 and 3 times 10 to the negative 6, and divided by distance between the charges squared. And this number hasn't changed. Because of the Newton's third law, the magnitude of the force acting on charge 1 from charge 2 is equal to the magnitude of the force acting on charge 2 from charge 1. And I did it again. No? What did I do? Two, 1 now is positive because it points to the right. Now minus 2, 3. 9 times 10 to the 9th. Charge number 2 has magnitude of 4 microcoulombs. Charge number 3 has magnitude of 7 microcoulombs. But total distance now between the charges should be equal to the sum of 0.2 and 0.15, which is 0.35 squared. Checking. So force between 2 and 3 acting on 2, repulsion to the left. From 1, attraction to the right. 1 and 2 to the right is positive, 2 and 3 to the left is negative. Well, now we just have to finish the calculation. Wherever it is going to be the answer. If the answer is positive, net force points to the right. But if the answer turns out to be negative, that means the actual direction of the net force is to the left. That's it. This is math. And you can do it. This is where I write. Meaning, I'm done, I've done my job. And I'm going to skip this. You can do it at home as an exercise. Question. In this situation, we have two objects, two balls. One is attached to a rod. Second is attached to a string. And the string makes the ball, the string makes an angle between the vertical direction and the answer to this question is in the Freebody diagram, of course. So that's what your immediate goal right now is, to draw a Freebody diagram for the ball attached to a string. So, of course, this is the initial situation. Let's make it completely identical. This is the initial situation when nothing except the string and the earth was acting on this ball. But now we did something. And what we did has a name, charged. Both of them. And after that, this ball moved closer to the second ball. We observe some deflection. And we can calculate the angle. And that will be our next goal. But for now, all we have to do is answer a question about polarity. And I'm going to start drawing a Freebody diagram for which object? For the ball on a string. The Freebody diagram for the ball attached to the rod is simple and not helpful at all. Here we have only force of gravity pointing down and the normal force pointing up. But for the ball attached to a string, the diagram now has to show how many forces. How many forces? 3, because we are adding one force to gravity and tension. So the gravity still points down because it always does that. Force of tension always points along the string. But if we only had two forces like that, the ball wouldn't be in equilibrium. So there must be a third force. And as you know, the third force are not Democrats or Republicans. So, clearly, the second ball attracts the ball on a string. Yeah. And that attraction only due to fact that these two balls must have opposite polarity. But which one? Is it a positive and this is negative? Or this is negative and that is positive? Do we know? No, we don't. There is no information about that. So, what's the right answer? Number 5. We don't know the exact, but definitely opposite. But now with the Freebody diagram, of course, let's see. Yeah, we can solve the problem. Uh, so, force of gravity, force of tension, the force of Coulomb's attraction, or we call it electric force. We have two options, mathematical options. We can use a component method. To do that, we have to introduce two axes, x and y. And since it's in equilibrium, the net force relative to x-axis has to be equal to 0. The net force acting on this ball relative to the y-axis has to be equal to 0. And that will give the answer. The second approach is geometrical. And we used all those approaches. So, and it was represented on this slide because we know how to add vectors, a tail to a head rule. We can add these arrows together. Net force as a vector has to be equal to 0. Hence, tension plus gravity plus electric force together equal to 0. A tail to a head rule says we have to do this. We have to draw one arrow, then we have to add a second arrow to it, and then we have to add the third. If you've taken PY106 and you haven't taken PY105, you don't know what it means. But you know, what does it mean? If I just walk around drinking my coffee, what does it mean? Mistake. There's a mistake. What did I do wrong? How do I fix it? Anybody? By the way, according to a tail to a head rule, if we start from this location and we finish at this location, we have to draw the arrow which represents the resultant. That's what a definition of a resultant is. It is an arrow which connects the initial and final locations. And the resultant, we can call it, I don't know, sigma. Must be equal to 0. Is it equal to 0? No, it's not. How do we fix it? We have to redraw the picture. How do we redraw the picture? Well, this is how we redraw the picture. Well, sorry. I forgot. It's a very important action. Wrong. How do we redraw the picture? This is how we redraw the picture. Yes or no? What do you think? You moved? It's you now? How do I fix it? What did I do wrong? What's wrong with that? The arrow, which is supposed to be horizontal, is not horizontal. So I violated the conditions of this problem, which means this is what? Wrong. And this is how science works. If you didn't succeed first time, you try again. But trying the same things, expecting different results, is not wise. So, okay, now everything looks right. This is an arrow which represents the force of tension. This is an arrow which represents the force of gravity. This is an arrow which represents the electric force. And we know from our everyday experience that vertical direction and horizontal direction are perpendicular to each other. If we don't know that from our everyday experience, we couldn't solve this problem. But now, if we look at this picture, what do we recognize? That's a very special shape, right? Yes? I only can see your lips moves. Because this shape has a special name, right triangle. And if we know right triangle, and we know everything about right triangles, now we just can apply Sokotoka and anything else, Pythagorean Theorem, calculate anything we want to. Well, first, of course, we need to calculate actually, I think we may even have extra values. Anyway, let's see what I have on the next slide. Empty room. Okay, so a triangle. Tension. Gravity. Electric. mg has to be equal to, well, 0.1 times 10. We have to use International System of Units. Always check units, which is 1 Newton. Electric force is supposed to be equal to 9 times 10 to the 9th times 3 microcoulombs squared. It's the same charge. Distance has to be converted into meters, 0.3 squared. Just out of curiosity, this is 9 times 10 to the negative 12, and this is 9 times 10 to the negative second, 0.33 times 10, yes. So now we can collect the powers. 9 and 9 cancels, 9 remains. It's going to be 10. 9 minus 12 plus 2, right? Which is 9 times 10. Negative 1. Negative 12. Negative 1.9. Okay, seems right. You have to check my calculations, because everybody makes mistakes. Mistakes are inevitable and unavoidable. What now? Well, now, Pythagorean theorem tells us how to calculate tension. It has to be equal to square root of electric force squared plus mg squared, wherever it is. And we can calculate this angle by, for example, applying a tangent equation, because tangent of this angle is supposed to be equal to the ratio of electric force over the force of gravity. Now I believe I have the answers. Yes, I do. So this is, again, 95% is PY105, and only little comes from PY106, the equation for the magnitude of electric force. Well, another example. Again, we have 3 charges, but now they're not aligned on the same line. So we got to do some geometry again. Very similar geometry, but let's do it just to refresh. Oops. I forgot to end. Okay. So what do we have? We have 9, 2, and negative 4. Nine nanocoulombs. 2 nanocoulombs, negative 4 nanocoulombs. We know the angle and the distance. Meters, yeah, and 30 degrees. And because this angle is 30 degrees and this angle given as a right angle, this angle will be equal to 60 degrees. Now we have to start drawing Freebody diagram for the charge on the right. Yeah, it says calculate net force acting on that charge. So that charge on the right experiences two forces, so we have to draw each. Well, the charge on the right is being repelled by the positive charge away from the positive charge. And when we do that, for the moment, we just forget about the existence of this charge. We look at a pair of charges, they repel each other, repulsion. But this charge now also is attracted to the negative charge. So we have to draw a second arrow. A second arrow which represents the force of attraction. Now we have to call them. We can call them again the charge number 1, the charge number 2, the charge number 3. In this case, this arrow represents force on first from second, and this arrow represents the force on the first from the third. How do we calculate these forces? Coulomb's law. The magnitude of the force acting on the first charge from the second should be equal to 9 times 10 to the 9th. Now, this little prefix nano means 10 to the negative 9. So this is 9 times 10 to the negative 9. And the second charge is 2 times 10 to the negative 9. And we have to divide by the distance between the charges. R1, 2. And, well, we have to find it. We know the hypotenuse. The hypotenuse, we can call it R2, 3, is equal to 3 meters. So R1, 2 should be equal to the hypotenuse, which is R2, 3 times cosine of 30 degrees. And that is equal to 3 times, anybody? Cosine of 30. Your calculator is in radians. Absolutely right. That's what I was waiting for. You don't have to know this, but it saves time. The exact value is square root of 3 over 2. The approximate value is 0.867, etc., etc. But this is a very time-saving technique because this distance has to be squared. So when we square it, we get rid of all the roots. Okay. Now we can write the magnitude for the second force, and that has to be equal to 9 times 10 to the 9th, same constant. We are multiplying two charges, well, magnitudes of those charges. 4 times 10 to the negative 9, 2 times 10 to the negative 9. And well, this distance, R2, 3, will be equal to, no, this is this R1, 3, 1, 3, is equal to the hypotenuse times sine of 30. Well, sine of 30 is 1/2, so 3 times 1 over 2. 3 times 1 over 2 squared. Let's say you know these numbers. What do you do next? Well, these two vectors form a triangle. So first of all, if we need to calculate net force, F net, again, it has to be equal to the vectorial sum of two forces, F12 plus F13. And again, we have two options. We can choose X and Y axes like this or like this and use the component method. Or we can add vectors together using a tail to a head rule. So it means we should add this plus this, and that gives this. This red arrow represents the resultant, the sum, the net force. Well, this is a special case when the angle between the forces is 90 degrees. So again, we have a right angle triangle. And what do we do about right triangles? Everything. For example, if we want to calculate the magnitude of the net force, we have to apply the Pythagorean Theorem. We cannot just add numbers. And I've seen people doing that. I've seen people writing F net equals F12 plus F13. That wouldn't work. You have to look at the diagram and use the trigonometry. Well, any questions? This is the general strategy. Works for any problem with any number of charges. All right, so that's not a question for the WebAssign, just let's reason through. What we know is that the red ball is positive. That's the first fact. And the second fact is the third ball on the right is in equilibrium. What does it mean in equilibrium? It means net force acting on this charge must be equal to 0. And the question is, what is the polarity of the first charge on the left? Is it positive? Is it negative? On one hand, it might seem we have not enough information because we don't know if the third charge is positive or negative. Could it be positive? Yes, why not? Could it be negative? Yes, why not? We have no information. What does it mean? It means we have to explore both cases. First, we have to assume it's positive and then make a statement about charge number 1. Then we have to assume Q1 is negative, Q3 is negative, and make a statement again about the charge number 1 and see if it makes any difference. So that's the strategy. Now let's apply that strategy. So let's say the third charge is positive. It means that charge number 2 repels it, which means the force acting on the charge number 3 from the charge number 2 points to the right. In order to cancel it out, to make net force to be 0, the force acting on the charge number 3 from the charge number 1 must point to the left. So, in order to have the force acting on this charge from that charge directed to the left, it has to be, you have to finish this sentence, negative. It has to attract the positive charge. Okay, negative. Now we have to try case number 2. The charge in the middle still is positive. We assume that the charge number 3 now is negative. What does it mean? You should draw the forces now. I'm going to give you a minute. Try to repeat the same strategy I just used for case number 1. Draw forces. First, you have to draw the force acting on this charge from that charge. Then you have to draw a force which would cancel out the first force. And then you have to make a statement about the polarity of the first charge. And you can talk. You don't have to whisper. And I'm going to check what is happening on the website. By now, you already should have transferred all the picture from the screen into your notebook. That's what you should be doing. Now, I want to ask a question. If you're using iPhone and iPad and have difficulties again today, please raise your hand. 1. Okay. Just in case, please send me an email about it, so I would know. Now, so, please, if you finished, you should know that the charge on the left, the charge number 1, now is negative again. So what should we have done? First. Now, the charge number 2 attracts the charge number 3. To cancel it out, the charge number 1 should repel the charge number 3. And repulsion means charge number 1 and charge number 3 should have the same polarity. If the charge number 3 is negative, charge number 1 has to be negative. But it turns out it doesn't really matter if the charge number 3 is positive or negative. In order to be in equilibrium, the charge number 1 must be negative no matter what. Which actually means that the net force is not just property of this charge, it's a property of the location of that charge. We can place a positive charge at that location, we can place a negative charge at that location, and they will not feel any net force. All right, so let's calculate now the magnitude of the charge number 1. So we know the magnitude of the charge number 2. It's 2 nanocoulombs. We don't know anything about charge number 3, but we know now it doesn't matter. So if it doesn't matter, again, we just make any assumption about the charge number 3. Let's make it positive. Draw a Freebody diagram. The Freebody diagram says the repulsion due to charge number 2 and the attraction due to the charge number 1. And since net force acting on charge number 3 equals 0, it means the magnitude of the force acting to the right should be equal to the magnitude of the force acting to the left. What law do we use for the magnitude of the force acting between two charges? The Coulomb's law. If we have to calculate two magnitudes, we have to apply the same law twice. K Q3 Q1 over distance between charges 3 and 1 squared. K Q3 Q2 over distance between charges 2 and 3 squared. That's it. First of all, what we see, we can make it simpler. Every time when we can make an expression simpler, we have to. That's the law. So how can we make it simpler? Cancel k's immediately, and where else? Q3. So now we can rewrite this expression. Magnitude of Q1, that's what we're looking for, divided by, well, this distance, whole distance, given in terms of some r, 2r plus r, 3r squared. What did I do wrong and how to fix it? Why? Because I have to square the whole thing. Has to be equal to, well, 2 nanocoulombs divided by, and the distance now is equal to just r squared. And now we can see we can make this expression also simpler by canceling what? R, yeah. So, and that gives the magnitude of this charge. What is it? 18. No, that's not me. 18 nanocoulombs. But we know the actual value should be negative, right? Questions, please. I think I have, okay. Yeah, this is the ratio of these charges. And 9 times 2, 18. And an opposite problem. Now we need to find a location where should we place the third charge so it wouldn't feel any net force. Okay, so the x-axis, we know two specific locations. At the first location, we have charge number 1, which is equal to 3 microcoulombs, and at the second location, we have a charge number 2, which is equal to 5 microcoulombs. We know that the value, the magnitude of the third charge, which we have to place, doesn't matter if the location where we place is such that there is no force acting on it. So the question is, where should we place it? And in general, we have 9 options. We can place it here, 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 or here, here, here. Because this line and those 2 locations divide the whole space, the whole plane, into 9 independent regions. And what do we have to do? We have to check each of them one by one. I am not going to do that. I'm going to check only a couple. For example, this one. Let's say I'm placing the charge number 3, which is equal to, and now we use the fact the value of the charge doesn't matter. So we can pick any convenient number. For example, 1. So this charge will be repelled, and repulsion means away, yeah, from the first charge. But this charge also will be repelled, and repulsion means that force points away from the second charge. So these 2 arrows represent individual forces. So if we add them up together using tail-to-head rule or parallelogram, this will be net force. Is it 0? No. So, wrong choice. And now we move on to the next. And this is what you should do at home to practice. And now I want to check this point. Again, I can imagine I am placing a positive charge here. So it will be repelled by the charge on the left. This arrow represents a force acting on the third charge from the first. But it also will be repelled by the charge on the right. This arrow represents the force acting on the third charge from the second. And because net force here must be equal to 0, hence these 2 forces must cancel each other out, meaning they must have the same magnitudes. Nothing new so far. Of course, now we have to start applying the Coulomb's law, right? K, Q3, Q2 over. Well, we have to introduce the unknown. This is the distance we are looking for. Let's call it, I don't know, R, just an R. R squared should be equal to K, Q3, Q1 over, and now it's supposed to be a different distance, this distance. Distance between the charges. But it's not R, and it's not 40. It's 40 minus R. And we can use, we can use centimeters here. At this point, it doesn't matter. And that gives an equation which we have to solve. Let's see what I have on the next slide. Next question. Yeah, okay. I'm going to add an extra slide. So again, first we have to simplify this expression by doing what? By canceling the constant, by canceling the charge number 3, because it doesn't matter. So what's left now? Q2 over R squared is supposed to be equal to Q1 over 40 minus R squared. And if you have taken PY105, you had to solve a very similar problem, but instead of charges, we used masses. And here we have a fork. We can use a quadratic formula because it's a quadratic equation. But sometimes there's an approach which is easier and faster. What does make this equation complicated? Squares. How can we get rid of a square? Unsquare it. So that's what we can do in this situation. We have to try. If it works, perfect. If it doesn't, we can always go back to the quadratic formula. So what we have is immediately a linear equation in centimeters. Now we can just cross multiply, so 40 minus r times square root of this charge should be equal to r times square root of that charge. We use magnitudes. And now the simple linear equation can be solved in a couple of minutes. You have to finish it. I think you have a similar problem in your homework. So it's a good practice. All right. It might be the last question for today. Please read the problem and find the difference between this problem and problem we just have solved. Same x-axis, same locations. What is the difference? One charge now has become negative. Does it make a difference? Yes, it does. So how do you approach the situation? You have to draw a picture. The picture looks exactly like the picture which was used with only one change. That's the x-axis. 0, 40 centimeters. So we still have a positive charge located at the origin. However, this second charge, Q2, now is negative and equal to -5 microcoulombs. And of course, intuition tells us first to check the same point we used before in the middle, or between the charges at least. And we can check what would happen for a positive charge. A positive charge located between the charges will be repelled. From the left, but will be attracted to the right. And it means the net force here actually will be stronger. Net force is not 0. So this location doesn't work anymore. All locations around don't work anymore. So technically what you need to choose from is somewhere here to the very left or somewhere here to the very right. This is basically only two reasonable choices. And there's a clue here in numbers. Because if we locate a charge very close to a strong charge, that leads to a strong interaction between these. So for example, if I place a positive charge here, it will experience a strong attraction to the charge number 2, but not as strong repulsion from the charge number 1. because here it will be very close to a strong charge and far away from a weak charge. So this also doesn't work, and by elimination, what's left here? Somewhere. Where? We don't know. So we introduce an unknown and we solve it. We've seen several examples which tell us that sometimes the actual value of a charge doesn't matter. What matters is the property of space at the location of the charge. So in physics, if something is important, first we give it a name, second we start to study. And the name which describes the fact that the property of space might change from location to location and might affect charges differently has a name electric field. So if we want to study electric field, what do we have to do? We have to take a charge to test the presence or the absence of the electric field. The charge which we used to test has a name, test charge. So we take like a tiny plastic ball, rub it with a piece of fur, we know it becomes charged. We attach it to a string, and now we just walk around and look. If the string is vertical, it means only two forces acting on it, gravity and tension, nothing else. But if we move to a certain location and suddenly we see some deflection, like in the problem before, that means there has to be the third force now starting acting on it. Not Republicans, not Democrats. And what is the nature of that force? Well, if we rubbed this ball with fur and we know it's charged, the nature of that force has to be electric. So if we see deflection, we say here at the location of this charge there is electric field which is responsible for the existence of this electric force. Of course, now we have to make an official definition. How would we measure, how would we calculate that new property of space, which we just named field? That's an official definition. We have to take a test charge, we have to know its value, and then we have to measure the force acting on this test charge at this location. For example, using a protractor, measuring angle. And if we know these two values, force acting on a test charge and the actual value of this test charge, this ratio by definition is called electric field at the location of this charge. That's it. That's a definition. Since we talk about definitions, what is a definition? What is a definition? It's not just something we define, it's a little bit more than that. And some people know, because we had a discussion about that, it's not just something defined by someone, it's also which everybody agrees upon. Because if you disagree, that's not a definition. So a definition doesn't require understanding. It's like learning a language. Yeah. Stall, table, electric field. That's it. It requires just memorizing and then application of that definition depending on the situation. And of course, as many physical quantities, it has a special unit, and the unit comes from definition Newton divided by Coulomb, has no special name. It has a different version in the future, we'll learn it, but for now, if we calculate or measure this new physical quantity electric field, we have to write a Newton over a Coulomb. That's it. According to this definition, the easiest situation happens when test charge is equal to 1 Coulomb. If test charge is equal to 1 Coulomb, that means electric field is just equal to force acting on 1 Coulomb charge. So if someone asks you how to calculate electric field, you have to say, all I need to do is calculate force acting on 1 Coulomb charge. That's it. It's going to be the same thing. That's a statement. Now we're going to use this statement. Don't answer this question. I have no time anymore. So let's just reason through. This arrow represents a force. How do we know? We can read. So this arrow represents this variable. The question here is about this variable. What is the relationship? The test charge. Well, a test charge, as any charge, can be positive or negative. This turns out to be negative. So this is what we have to do. We have to do geometry. We are looking for this arrow, which has to be equal to this arrow divided by a negative number. And to show explicitly that it is negative, we can use this symbol, -1 times magnitude. Or we can rewrite it mathematically like this. A negative number we have to multiply by a certain arrow. What does it do to an arrow? Flips it, changes the direction to the opposite, equals something opposite. So this is an illustration of a very simple fact. Electric field and force might be parallel or opposite. When? Well, this is actually how every textbook writes this expression, because we don't like fractions. We just convert it into multiplication. So, and from this expression, which relates a charge located somewhere, electric field acting on that charge at that location, and the force generated, provided, exerted by that electric field. Because we are multiplying a vector and a number, the result depends on the number. If the charge is positive, these two vectors always point in the same direction. But if this charge is negative, these two vectors always point opposite to each other. That's it. What's happening here? Well, a test charge is placed in a region with a certain electric field. And these lines just represent the presence of electric field. And because of this electric field, charge moved in a direction opposite to the field. So here I can draw an arrow which represents the existence of electric field at the location of the charge. But I also can draw an arrow which represents the force acting on it, electric force, because also we have tension and gravity, no doubt, but electric force must point to the right. If I look at this picture, that immediately tells me this charge must be, what do you say? Negative, yes, of course, negative. And I just did the Freebody diagram. Let's do it one more time. Tension, electric force, gravity. Now, these are specific values we can use to solve the problem, but first I want to point out when we write an equation, we must be able to say out loud, absolutely clearly, what does each variable represent. So if you write this equation, which relates a force, a charge, and electric field as vectors, this variable represents the actual value of the charge. Actual value could be positive, actual value could be negative, well, even zero, so force would have been zero. But if you want to solve a problem, we will have to use magnitudes. So let's solve the problem. In this in this situation, again, we can use the component method. For that, we have to introduce x-axis, y-axis, etc., etc. Or we can use, again, the tail-to-a-head rule to add 3 arrows. Tension force plus electric force plus force of gravity together should give the net force, which in this situation equals 0 because the charge, this charged object charge, is in equilibrium. So we know what to do about it. We can add all these arrows by tail-to-a-head rule, and that gives us a right triangle. Again, in this right triangle, the hypotenuse represents the magnitude of the tension, vertical side mg, horizontal side electric force, and the magnitude of electric force is equal to the magnitude of charge times the magnitude of field. But only strange people, like I am, always write explicitly vertical bars. Regular people would write this equation like this. But in this equation, the same letter Q has a completely different meaning. It's not an actual value of a charge anymore. It's the magnitude. So if you confuse your own notations, you may make a mistake. So every time when you write an equation, you have to know exactly, and you have to be able to say exactly the meaning of each variable. What does it represent here or there? Is it the actual value? Is it the magnitude? Is it a vector? Is it a component? Is it absolute value of something? Well, now we are done. This is a 45 degrees angle. How do we know? We have eyes. Which means this is a 45 degrees angle, which means in this triangle both sides are equal to each other. So mg is equal to q times e, and in this case q represents the magnitude, and what are we looking for? Q will be equal to mg over e, hence 0.1 times 10 over 100.01 coulombs. Now we have to remember, in this expression, Q represents magnitude. The actual value must be negative because we said so 2 slides ago. So the actual answer is negative 0.01 coulombs. Any questions? So a reminder, same variable might have different meanings. You know what? Now I want you to answer this question. It has to be now question 5 because I skipped it. Please just solve this problem and choose the answer which corresponds to your final number. You have a positive charge. The magnitude equals 10 nanocoulombs. And 30 centimeters from that charge, you're calculating electric field strength. We don't never say strength, we just say field, E field, the shortest way to say it, E field, that's it, which represents the whole sentence, the electric field strength of electric field generated by some other charges at this location. And this is what you can use. If you want to calculate electric field, all you have to do is calculate electric force acting on positive 1 Coulomb charge placed at the location of your analysis. So you have to write an equation. Electric field strength is equal to the magnitude of the force acting on a 1 Coulomb charge. So what do? Well, you imagine there is a second charge, a test charge located 30 centimeters away from the source of the electric field. How do we calculate the force? You know that you have to apply the Coulomb's law. Coulomb's law says use the constant, use the magnitude of the first charge. And what should I write for the second charge? What number? What number? For the Q2. 1, because that is how we're calculating electric field strength. It is equal to the force acting on 1 Coulomb charge divided by the distance squared. So what do we have? 9 times 10 to the 9th, 10 to the negative 9, and 0.3 is 3 times 10 to the negative 1, so 9 times 10 to the negative 2. Can we make it simpler? Yes, we can. 9 and 9. 10 to the 9th, 10 to the negative 9th, 10 to the 3rd, and Newton over a Coulomb. However, this exercise is much more important than just calculating this particular strength, because we can apply the same strategy for any charge and any location. What do we have to do? This is what we have to do. Electric field strength is equal to the magnitude of the force acting on a 1 Coulomb charge. So if I have a source charge, let's call it Q, and if I have a test charge, which equals 1 Coulomb, applying Coulomb's law says Q times, well, magnitude of Q times 1 over distance squared, and anything times 1 is just same thing. So this expression tells us how to calculate the magnitude of electric field strength generated by any single charge. That's it. That is why this expression has a name. The electric field strength of a point charge. Yes? The Q is the source charge. The source charge. Source charge generates this electric field, is responsible for the existence of that electric field. And electric field, again, is a name for changing property of space around it. If we have a charge, it changes properties of space around it. How? How does it change? It changes in such a way, so if we take another charge and bring it into this field, it will experience a force acting on it. And the electric field, like a mediator between charges. One charge or many charges generated other charges, feel it, test it. Well, have a nice 4th of July. That's the last slide for today. This is how we can calculate electric field strength generated by a single charge. And I sent an email today that we have to close today at, well, offices close today at 1 p.m. So office hours will last from now to 1. After 1 p.m., there will be no office hours today.
So I answered number 5 accidentally, and I answered number 6. Would this be all right?
That's fine.
So I was just wondering, so the electric field, right? It's like similar to the gravitational field, right?
Absolutely.
So using that like analogy, let's say if like the center, let's say the mass of the sun was all condensed into like a small point,
Yes.
and then it was like, let's say this much above Earth, would it also be accelerating down at 9.8 meters per second squared?
Yes.
Okay.
But the Earth would be accelerating toward it with much higher acceleration.
I'm just wondering.
So lab will be Friday.
Thursday, Friday.
Okay, and do we have any pre-lab
No.
things? Thank you.
Yes.
For the web login, when we're putting in answers, so I first want to ask, like, how many digits should we go to?
My advice is, if you keep like 4 digits after decimal point, you should be fine. You don't have to do more. It's probably 1 or 2 problems out of all problems which might require a little bit more accuracy. But you have 6 trials for each part of each problem. So if you try a couple of times it doesn't work and you can convinced everything was right, most